Alright, so now we're going to look at some incomplete neutralization problems. And the first one we're going to look at, which are much easier, when you have a strong acid and a strong base. So it says, calculate the pH after mixing 440 milliliters of 0.25 HCl with 30 milliliters of 0.25 NaOH. So as you can see, I wrote the reaction. Again, this is a strong acid, strong base, so it always produces a salt, which doesn't produce any acids or bases and water. Okay, and the first thing we have to do, we don't know if this is neutralized. We don't know if these are equal moles. So we're going to calculate the moles using the molarity equation of NaOH and of HCl. So if you look, I put the 0.25 for the NaOH, and the 30 for the 30 milliliters for the HCl, and I solve for X, which is the moles, and you multiply, cross multiply, and if I bring the shade down, you get 0.075. And I did the same thing for the moles of HCl. So it's 40 milliliters, and it's 0.25 HCl, and you get 0.01 moles when you do that. Now, if we look at this reaction here, okay, this is a 1-to-1 reaction. So one of these is the limiting, okay? And it turns out that NOH is the limiting. This is less. So all of this is going to be used up, right? Because it's less than this. And there's going to be some HCl left. Well, how much HCl left? Well, it's a 1-to-1 relationship, right? So if we scroll down, all of this is going to react, right? And what's left is going to be 0.01 minus that, which is 0.0025 moles of HCl. Now, so all of this is going to completely react. All of this is going to be turned into salt and water, and there's some acid left. Okay. Now that acid is going to make the pH that's left is going to make the pH go down. Okay. Well, how much? Well, we know we have 0.025 moles left, and to get a H+, we have to use the negative log of the hydrogen ion concentration. Okay. But this here is moles, and we have to get a concentration, okay? So we need to get the liters. Well, we poured these two solutions together. So the total volume is 70, and we have to convert that to liters, so that's 0.07. And when you do that math, when you get the 0.07, this is this molarity. When you divide this divided by that, you get this. So this is the molarity of HCl left, okay? And then again, HCl completely dissociates, so all of that's going to be H+. And you put that in the negative log equation, and you get a pH of 1.45. So when you're doing strong acid, strong base, incomplete neutralization problems, you have to find how much of either acid or base is left, the moles. So you find the moles first, find which one is limiting, and then find out the amount of acid left by subtracting the bigger from the smaller. Then you're going to get the moles of whatever of the excess, divide it by the liters of solution, and then you're going to get the molarity of the acid left or the base left, and then put that molarity, since it completely dissociates, into the log of the hydrogen ion concentration. So the problem that we looked at the previous problem was when you have a strong acid and a strong base. We're now going to look at an incomplete neutralization problem when you have a weak acid and a strong base. So here we're mixing, they want to find the pH after we're mixing 25 milliliters of 0.2, this is acetic acid, which is a weak acid, with 40 milliliters of 0.10 sodium hydroxide, which is a strong base. And then here they're giving us the Ka of, which I forgot to give you, so I wrote it in, the Ka of acetic acid, which is 1.8 times 10 to the negative 5. Now the process is the same, okay, except at the end you can't put the concentration into the log directly because this, whatever's left of this, won't completely dissociate. So if you take a look, I wrote the reaction. This is nothing new. So this loses this H, right, and gives it and combines with the OH here to produce water, and then the Na combines with this. So the Na combines with what's left, which is CH3COO negative. And forms this salt. Okay, now, like I did in the previous problem, I found the moles of acetic acid, Again, using the molarity equation, converting this to liters and putting that in there and finding moles. So I found the moles of that. And I also found the moles of NaOH, using these same values and putting them in there. So I would do that. I would make sure you know how to do that. Now, if we take a look again, the reaction is 1-to-1. Okay? So here, the NaOH is going to be limiting because there's less of it, and it's a 1-to-1. So I'm going to subtract to find out the amount of acetic acid that I'm going to have left. And if I do that, 0.005 minus 0.004 is 0.01 moles of acid. Okay, now, what that acid, this vinegar, the vinegar that's left, okay, so again, all of this has been neutralized. Okay, all of this is reacted, and we have some acetic acid left. What is this acetic acid going to do? Well, if we look here, the acetic acid, which that's left that hasn't reacted, is going to react as an acid and produce some H+. Okay? And again, that's going to make the pH not be neutral. Well, how much? Okay, well, we just found out that'd be 0.001 moles of acid, so we have to find the molarity of that. Okay, and the molarity of that, we have to add the volumes together. So we add 0.25 and 40. We add those values, and we get 65. And we have to convert that to liters. And so I divide the moles of acid left divided by the volume of the solution, and I get that molarity. Now, in the strong acid, strong base problem, we could just put this directly into the log because it completely dissociates. But this is vinegar, or acetic acid, is a weak base, so we have to use the Ka. Now, if we look at the equation for the Ka, ignore this for a second. This is the down here. This is the expression for the Ka for this reaction here. So we have the amount of acid left, right? This is the amount here. We have the amount of acid left. So we can put that into the equation. And we need to find the H+, which is what we're trying to find. We need to find the amount of the conjugate base that's left. Well, if we go back up to the equation that's here, we know that 0.04 of this reacted. So that means it's going to produce 0.04 of the conjugate base. So, again, we need to convert that to a molarity. So here's the 0.04, okay, divided by the total volume of the solution, which is adding the two together and converting to milliliters. And then we get this concentration. And we can put that in for this part of the Ka. And it told us in the beginning of the problem, where I wrote it down, that the Ka here is 1.8 times 10 to the negative 5. Using algebra, we can solve for the concentration of H+. If I do that, I get the concentration of H+ is 4.5 times 10 to the negative 6. Okay? And then I can, now that I have the H+ concentration, I can put that into the negative log equation and get the pH, which is 5.35. So again, when we're doing these problems, the first steps are the same. Find the moles of both of them. Find the amount of excess reactant by subtracting the bigger from the smaller, and then convert that to molarity by dividing by the total volume. Okay. Now, if it's a strong acid or strong base, you can just put this directly into either the POH or the pH equation. If it's a weak acid, okay, you have to find the amount of conjugate base that is produced, and that's the same as the the limiting of this. Convert that to a molarity, and then put it into the Ka, and then solve for the hydrogen ion concentration, and then you can put that into the log equation. Okay. On the homework, there's an example. There's one of each one to do. All right. Have a good weekend. Stay safe in the snow.